Welcome to the pH and pKa video. By the end of this video, you should be able to predict the protonation state of a molecule by comparing the pH of the solution and the pKa of the acid. You should understand how acid-base indicators work, and you should be able to select an appropriate acid-base indicator based on pKa values. So first, let's start with some vocabulary. What does protonation state mean? Recall that when we're dealing with acids and bases, we also often refer to H+ ions as protons, because essentially once a hydrogen atom has lost its electron, it's a proton. Therefore, its protonation state describes whether or not the acid has the H+ or the proton attached or not. So here we have carboxylic acid in its protonated state because the H+ is bonded to the molecule. And here the carboxylate ion is in the deprotonated state because it does not have the H+ bonded to it. We can make determinations regarding the protonation state of a molecule by looking at the Henderson-Hasselbalch equation. Recall that based on the Henderson-Hasselbalch equation, when the pH equals the pKa, that means that the concentration of acid and its conjugate base are equal. Recall, for the pH to equal the pKa, this term would have to drop out. That happens when you take the log of 1, meaning that A- and HA are equal. Therefore, we can say that at that point we have equal concentrations of the protonated and deprotonated state. When the pH is less than the pKa, that means that the concentration of our conjugate base is less than that of our undissociated acid. Thinking about this mathematically, if the pH is going to be less than the pKa, that means that this term must be negative. That only happens when the numerator is smaller than the denominator. Therefore, when the pH is less than the pKa, we say that we have more of the protonated form in solution, more of the HA. One way to think about it is that when the pH is less than the pKa, there's some extra H+ ions floating around, and they protonate the acid. The opposite is also true. When the pH is greater than the pKa, that means we have a higher concentration of conjugate base than we have acid. This means that more of the deprotonated form is in solution, more of the A-. Again, thinking about this mathematically, if pH is going to be greater than the pKa, this term here must yield a positive number, which happens when the numerator is greater than the denominator. Let's think about this in terms of a titration curve. Here we're looking at the titration of acetic acid. I've written the formula here. Here's the protonated state on the left, and then on the right, the acetate ion right here is the deprotonated state. Notice that when we start the titration, the pH is quite low, meaning we have much more of the protonated form versus the deprotonated form. As we start to convert protonated acetic acid into acetate by adding strong base, the pH begins to climb. Recall that halfway to the equivalence point, shown here, the pH will equal the pKa, meaning we have equal concentrations of protonated and deprotonated forms of the acid, equal concentrations of acetic acid and acetate. As we add more strong base and continue to deprotonate acetic acid, we start to see that we have more of the deprotonated state, more of the acetate ion. This is because now our pH is greater than our pKa, meaning we have more A- versus HA. The concept of protonated versus deprotonated states helps us understand how an acid-base indicator works. An acid-base indicator is essentially an equilibrium system between the protonated state of the indicator and the deprotonated state. What makes acid-base indicators special, though, is that the protonated state is one color and the deprotonated state is a different color. For instance, if this indicator were methyl red, it would be red when it's protonated and yellow when it's deprotonated. We can use Le Chatelier's principle to understand how this system works. If we add acid to this system, we're increasing H+, causing our equilibrium position to shift left. Therefore, we'll have more protonated indicator than deprotonated indicator, and the color will be red, which is the color that indicates an acid. On the other hand, if we add base, recall that the base, the OH-, will react with H+ to form neutral water. Therefore, we're essentially decreasing the H plus concentration and causing a shift in the equilibrium position to the right, therefore producing more of the deprotonated state and turning the solution yellow, which indicates a base. Now let's consider how to use this information to select an appropriate indicator for titration. The indicator should change color at the equivalence point of the titration. Recall that's the main function of an indicator in a titration, to indicate when the equivalence point has been reached. Indicators change color when their protonation state changes. Recall that this happens once we pass the point where the pH equals the pKa in either direction. Therefore, we should select an indicator with a pKa that matches the pH at the equivalence point. This will cause the color change to occur when the equivalence point is reached. As an example, here's a list of common indicators with their pKa's and change ranges. Notice that the pKa always corresponds to the range in which the indicator changes color. Looking at it on a titration curve, this curve shows two different titrations, the dark blue line indicating the titration of a strong acid with a strong base, and the pale gray line indicating the titration of a weak acid with a strong base. Notice that the strong acid titration will have a long equivalence point, meaning that it spans several pH values. This means that there are lots of indicators that are appropriate for a strong titration. In this case, both phenolphthalein and methyl red would be appropriate indicators, since they both change color in the range of the equivalence point. Weak acid titrations, however, have a much shorter pH span for their equivalence point. Therefore, only phenolphthalein in this case would be an appropriate indicator. Notice that methyl red would change color before the equivalence point is reached. Here's a few questions to try on your own. Pause the video here and answer these 3 questions using the indicator information on the right. When you come back, I'll reveal the answer. Welcome back. Here's what you should have gotten. For number 1, recall that strong acid, strong base titrations have a long equivalence point that generally spans several pHs. So phenolphthalein and bromothiamyl blue would both be appropriate. In fact, thymolphthalein may even work, although it would definitely be on the high end. For number 2, we're asked about the color of methyl orange in a solution with a pH 2. Notice that methyl orange has a pKa of 3.4, meaning it will switch from red to yellow when the pH equals about 3.4. Therefore, when the pH is less than 3.4, it will be red. And then finally, in number 3, we selected methyl red because its pKa is very close to the pH of the equivalence point for that titration. That brings us to the end of this video. Let's review our goals. First, we looked at how to predict the protonation state of a molecule by comparing the pH of the solution to the pKa. Recall that when the pH is greater than the pKa, that means that more of the deprotonated form is in solution, and then when the pH is less than the pKa, we have more of the protonated form in solution. Then we looked at how acid-base indicators work, and we learned to select an appropriate acid-base indicator based on the pKa value.